This video is on the individual gas laws that make up the combined gas law and on Dalton's law of partial pressures. So we've been looking at the combined gas law and how it compares pressure, volume, and temperature of a gas in one situation with that same sample of gases, pressure, volume, and temperature in another situation. Again, you'll know you need to use the combined gas law if you have two of something. So two pressures, two volumes, two temperatures. Now, if one condition is constant, like our temperature isn't going to change or our volume isn't going to change, or one of those conditions is not mentioned at all, it's going to drop out of the combined gas law equation. Now, it's important to know this because on your reference tables, you're given the combined gas law. And so we need to be able to come up with the individual gas laws from this one equation. So if temperature is constant, so our temperature is not changing, we're just going to see a relationship between pressure and volume. And we had this little animation that we saw before. You can see as volume goes down, the pressure goes up. So those gas particles are hitting the walls more often. And as the container gets larger, the particles are hitting the walls of the container less often. So our pressure goes down. So these two have an inverse relationship. So as volume goes up, pressure goes down. And it's important to remember that when you're working with these problems because you can go through a common sense check. So if our pressure goes up, our volume should go down. Our next one, our next condition being constant would be pressure being constant. Usually this is probably the most realistic of all of the gas laws. You'll run into this particular gas law where pressure is constant many times in your life because as I said before, we kind of live our lives under constant pressure. Now, pressure is constant, it's going to drop out, and this would be what your equation ends up looking like. Again, you would want to cross multiply to rearrange the equation. That just makes things a whole lot easier. Now, when we talk about this volume and temperature relationship, the best thing to think about is a balloon because we want to think about a container that has a flexible volume, and that balloon fills that bill. And so if I have a balloon, and I have it inside and I blow it up and I go outside and it happens to be cold outside, the particles are not going to be moving as fast. So they're not going to hit the walls as often. And so the balloon's going to start to kind of shrivel down and our volume will go down as the temperature goes down. Now, if we bring the balloon back inside to the warm air, the particles are going to start moving faster and they're going to make the particles hit the walls more often and the balloon will plump back up and increase in volume there. So here, temperature and volume move in the same direction. So as temperature goes up, volume also goes up. If volume is constant, your combined gas law ends up looking like this. Again, volume would just drop out of the equation. A lot of times when we're talking about constant volume, we're talking about a rigid container. So you can think about a spray paint can. When you spray a spray paint can, the gas on the inside of the can is under high pressure. And when you press the nozzle, it goes from high pressure to low pressure out in the atmosphere. And because our pressure is decreasing, our temperature is also going to decrease. So if you've done any spray painting, you might notice that your finger starts to get really, really cold. And if you do a lot of spray painting, you can actually end up with frostbite on your fingers just from being exposed to that cold of a temperature. Now, it's easier to think about the relationship between pressure and temperature in the same way that we looked at volume and temperature. So as temperature goes up, particles move faster, they're going to hit the walls more often. And so as temperature goes up, so does the pressure. All right, so those are the individual gas laws that go into making the combined gas law. And you can use the combined gas law as it is if you have all of those variables, or if one of the variables is constant, it's just going to drop out of the equation and it just makes it a little easier to work with. Okay, one more gas law to add to our list, and this is Dalton's law of partial pressures. So, partial pressure is the pressure that each gas exerts. And it's a pretty simple gas law, and it says that the total pressure in a container is equal to the sum of the partial pressures of the component gases. All right, so if I had a container, and let's just simplify this, that had hydrogen and carbon dioxide in it, those two gases. And I wanted to know the total pressure inside. Well, I would need to add the pressure of the hydrogen gas to the pressure of the carbon dioxide gas, that each one that's exerting. So this is it in sound effects. So hydrogen's a tiny little molecule. So when it hits the walls of the container, it doesn't have a lot of mass. So it's just tink, tink, tink as it hits the walls of the container. Carbon dioxide, though, is a huge honking molecule. It's got a molar mass of 44.01. And as it hits the walls of the container, it's kerplunk, kerplunk, kerplunk. And so to get the total pressure, you have to add the tink, tink, tink to the kerplunk, kerplunk, kerplunk. Now, the formula for that is given to you on your reference tables, and it says that the total pressure, so that's what PT stands for, total pressure, is equal to the pressure of the first gas plus the pressure of the second gas plus the pressure of the third gas, so on and so forth. So if we apply that in a problem, it's going to look like this. And so it says, what is the total pressure of a mixture of helium, nitrogen, and oxygen if they have these partial pressures? So we're going to plug that in, and normally we don't number our gases, but we will give it a notation instead of a number. So our total pressure is equal to the pressure of the helium plus the pressure of the nitrogen plus the pressure of the oxygen. So all we're going to have to do is add these together. One of the ways that you know you have to use Dalton's law of partial pressures is that you're going to be given a whole lot of pressures. And really, that's the indicator that you need to use Dalton's law of partial pressures. So in this case, if I add all these together, I get 852 millimeters of mercury. Now, oftentimes they will rearrange this type of question just to make it a little more difficult. And they might say, you have a total pressure of 852, your pressure of helium is this, your pressure of nitrogen is this, what is the pressure of oxygen? So if you plug everything in there, you just have to solve for the partial pressure of oxygen, which means you're going to add these two together and subtract them from that total pressure.